This section is about the indeterminate forms and the L'Hopital rule. We will try to evaluate a limit of the function at the point that the function is not defined. We do have 7 indeterminate forms. We have 2 quotient, we have product, we have difference, and 2 and 3 powers. In today's video, we will focus on the product. Before we start, let's look at the L'Hopital rule. Having function f of x and g of x, they might create a form of the limit 0 over 0 or infinity over infinity. One function will go to 0 and the other function will go to 0, and we will have a quotient of them, or respectively the same for the infinity. Then what we can do? We can apply, in order to solve this, the L'Hopital rule. The L'Hopital rule is telling me that the ratio, the limit as x approaches a of the ratio of the functions is the same like the limit as x approaches a of the ratio of their derivatives. That means the ratio of the functions the same like the ratio of the derivatives at that given point. And we have the proof in the previous video. Okay, that's me now, product. Maybe I can just say one more thing. We can only apply the L'Hopital rule for these 2 quotient forms. We do have the additional 5 indeterminate forms, but we always have to rewrite them in terms of the ratio and then apply the L'Hopital rule. Indeterminate product, we will see the limit of the product f of x times g of x at x as x approaches a. Okay, that's when we do have a product and one function is approaching 0. I mean, one function goes to 0 and the other function goes to the infinity. And we end up having the form 0 times infinity. 0 times any number is of course 0, but not in this case because infinity is not a number. Infinity is just a symbol indicating like a huge numbers. Yeah? And infinity is not equal to another infinity. That means 0 times something that is not, it's not defined, we can't really assume that is 0. Yeah? 0 times something that is not a number is not a number. That means what we have indeterminate form, undefined form at this point. Okay, but what we will do, we know that the L'Hopital rule can help. Before applying the L'Hopital rule, the product has to be changed for the quotient. But this is not a problem. We can use some algebra arithmetic tricks. Looking at this form for a few seconds, what could be the answer if we will have this limit? F of x times g of x, and of course 0 times infinity respectively. We may have, the answer could be 0. Let's say if the first function, if f of x is like winning stronger, we may have infinity or negative infinity if g function is taking a lead. Or we can also have some compromise between both of them, and the final answer will be a finite non-zero number. Okay? How can we rewrite a product in terms of the quotient? Of course, we can keep one function on the top of the fraction and we may flip the other one. Okay? And you may even realize function f was approaching 0 and function g infinity. Now 1 over infinity, 1 over big number is 0. As we can see, creating a quotient, we did create the indeterminate form, which is ready for the L'Hopital rule. You may do the other way, depends on the formulas, depends on the function. We may keep g and we may flip f function. G is approaching infinity, positive or negative, and f function is approaching 0. 1 over 0, 1 over small number is a big number. Also doing the other way, we got another form, indeterminate form, which is ready for the L'Hopital rule. Okay, let's solve a few problems. Evaluate a limit as x goes to the 0 from the right-hand side, x times natural log of x. X goes to 0, of course, from the right-hand side, but it's just 0, times, and logarithmic function at 0 from the right-hand side goes to negative infinity. Okay, I can draw the logarithmic function. That's 1 natural log of x, and we can see 0 from the right-hand side, function is going down. That's when we definitely have indeterminate product form. Let's rewrite as a quotient. In this case, I will keep the natural log function on the top and I will flip x, 1 over x. Let's double check. Logarithmic function at 0 from the right-hand side is negative infinity. 1 over 0, 1 over small number is a big number. Perfect. We are allowed to use the L'Hopital rule, and I will indicate with h. Now, after that, means that I will have the ratio of the derivatives. Derivative of logarithmic function and the derivative of rational function 1 over x. Okay, let's. Derivative of ln of x, 1 over x, derivative of 1 over x, negative 1 over x squared. And when we simplify, 1 over x times negative x squared over 1. Dividing by fraction means multiplying by reciprocal. Simplifying, I have just x because I can simplify. X goes to 0, 0. It means the answer is 0. But we definitely have a proof. We have a reason to pick 0. Example number 2. Evaluate limit as x goes to the infinity, x times e to the negative x. X goes to the infinity. Exponential, natural exponential function at negative infinity, of course, is 0. We do have indeterminate form. I can just draw the exponential function. Okay, that's function e to the x. And at negative infinity, we can see it's approaching x-axis, which is value 0. Okay, product, let's switch and rewrite as a quotient. In this case, it's easy to keep x, and rewriting without the negative exponent, we will have e to the positive x in the denominator. Let's double check. X goes to the infinity. E, the exponential function at infinity, is also infinity. Perfect. The L'Hopital rule. X, derivative of x is 1, derivative of e to the x is e to the x. And we do have 1. Exponential function at infinity is infinity. 1 over infinity, 1 over big number is a small number. The answer is also 0. Okay. Also, you remember, I can probably say this, having a limit at infinity, we can compare the growing rates, the relative growing rates. We have a battle between e to the x, exponential function, and power function. Of course, exponential functions grows much, much faster than this is sitting in the denominator. If the denominator wins, the answer is right away 0. You may also avoid the L'Hopital rule and just use that argument. And one more. Evaluate the limit as x goes to 3 from the right-hand side, x times x minus 3 times tangent of pi x over 6. Okay, that means function x minus 3 as x is 3 is definitely 0. And function tangent, when we substitute 3, we will have pi over 2. Tangent at pi over 2 from the right-hand side is negative infinity. We remember tangent, function tangent. Okay, tangent looks like that, 0, pi, and so on. Negative pi. That's a little bit too fancy. Okay, and it's not defined at pi over 2. And at the right-hand side, function goes down, negative infinity. Okay, let's rewrite this as a quotient. This one, we can't really compare the growing rates. It's not at infinity. Yeah, we will not do this. Okay, in this example, I will keep the linear function and flipping tangent and putting in the denominator 1 over tangent is actually cotangent. It means having trigonometric functions, it's worth to put them in the denominator. If it doesn't work, we can keep them. We can keep them on the top. Okay, let's check. 3 minus 3, 0. Cotangent at pi over 2 is actually 0. Okay, I think we are ready to use the L'Hopital rule. Please always check if you're ready. Derivative on the top is 1. Derivative of cotangent is negative cosecant square of the same angle times derivative of that angle. Derivative of pi over 6x is just pi over 6. Okay, now let's evaluate. This is 1. Negative will stay, which actually I can even put on the top, just not because this negative is not squared. Only cosecant is squared. Cosecant is squared. But I will rewrite cosecant as a 1 over sine, and substituting 3, we will have pi over 2. Okay, actually I can flip pi over 6, dividing by pi over 6 is multiplying by 6 over pi, and sine at pi over 2 is 1. 1 squared is 1. So the final answer is negative 6 over pi. And we can see we do have a finite number with this indeterminate form. Thank you.